Modbus RTU and Modbus TCP are two very different communication types. Modbus RTU is built for serial multi-drop RS-485 networks, and Modbus TCP is built for Ethernet-based networking. Because the physical layers are so different, the failures that you see in the field are different too. Things like wiring and noise issues on Modbus RTU, or IP and network issues on Modbus TCP. So whether you're trying to diagnose a current issue, or you're just trying to be proactive, we're going to be breaking down possible issues with both and how to design around them. First, we'll be starting with Modbus RTU over RS-485. One of the most common ways that Modbus RTU fails in the field is intermittent communication that feels random. You'll see something like timeouts that come and go, devices that respond sometimes but not others, or a network that looks stable until a motor starts. When you see that, it's rarely the Modbus protocol itself. It's usually the RS-485 physical layer. Don't get me wrong, RS-485 is robust, but it is sensitive to how the physical layer is implemented. Many RS-485 and Modbus RTU issues trace back to installation details like termination placement, topology choices such as long cable runs, biasing, and how shielding and grounding are handled. If any of those are inconsistent, you can end up with reflections, signal distortion, or an unstable idle bus state. And those problems often don't show up on a quiet bench test. They show up once cable runs get longer and the electrical environment gets noisier. So what do you do about it? Well, you would want to design the RS-485 bus like a bus on purpose. You'd want to keep it linear, control where termination happens, keep stubs short, be intentional about biasing, and be consistent about how shields and grounds are handled so you're not creating unwanted noise paths. Now, this is also where your interface hardware matters during commissioning and troubleshooting. A lot of teams will connect a laptop, a controller, or a temporary test setup into an RS-485 segment and then chase problems that are actually coming from the connection layer. If you need a stable industrial way to bridge into RS-485, that's the role of serial converters like ICP-DOS USA's ITM7561. This converter helps ensure the interface itself isn't adding instability while you're diagnosing the network. If you're interested in checking out this module, I will have the link below. The second RTU failure mode shows up as it breaks down when the plant turns on. You'll see timeouts that correlate with VFD activity, motor starts, welders, or heavy load changes. RS-485 cabling often ends up routed near power conductors, or it crosses noisy equipment, or it shares grounding paths that were never planned for communications. In that environment, the same network that looks fine at low noise can start dropping frames under real conditions. So the design move here is actually containment. Instead of one huge RS-485 trunk that spans everything, keep RS-485 segments short and local close to the devices. Then move your longer distance transport onto something that's easier to scale and isolate. That leads into the third RTU failure mode, one bad node taking down the whole bus. A loose connection, a failed device, or a damaged cable can all drag an entire multi-drop segment into a mess. In a large RTU trunk, everyone shares the same medium, so reliability becomes a group project. The fix is segmentation. You want failures to stay local, not propagate across the entire system. And this is where gateways become extremely useful, not just for conversion, but for making the system easier to manage. A stable architecture is to keep RTU close to legacy field devices, meters, drives, older PLCs, or remote panels, then convert that RTU segment into TCP at the panel edge. Now, your RTU is short and controlled, and your backbone is scalable. And again, the best way to do that is to use a Modbus gateway like the TGW700 series, which is commonly used to bridge Modbus RTU to Modbus TCP while keeping your mapping clean and your segments manageable. Again, if you're interested in checking out this product, the link will be in the description below. Now, let's switch over to Modbus TCP. The first way Modbus TCP fails in the field is almost never Ethernet is unreliable. It's IP planning or the lack of it. What fails is addressing mistakes, IP conflicts, and inconsistent commissioning habits. And this is what it looks like. Everything works during staging, then on site, a device disappears, or it works until a contractor plugs in a switch, or someone adds a new device and suddenly two devices are fighting over the same IP. Or you get a system that works on one laptop but not on another because the subnet assumptions are different. The design fix is kind of boring, time, but it works every time. Treat IP addressing like part of the spec. Decide early whether you're using static IPs or DHCP reservations. You should label devices, document subnets, and keep the addressing consistent across panels. Modbus TCP problems are often network hygiene problems, so the best preservation is a clean plan. The second Modbus TCP failure mode is what people describe as "it's the network." It shows up as intermittent dropouts that are difficult to reproduce. One day it's fine, then the next day your HMI shows stale values. Or values freeze for a few seconds, then come back. Or it fails only when connected to a facility network you don't control. Most of the time, this is caused by something outside of your panel. An unmanaged switch under load, a topology change, a marginal cable, or policies on the shared infrastructure. Even when everything is technically working, shared networks can introduce variables you didn't design for. Now, the design fix here is segmentation and ownership. If you can keep your control and monitoring network separate from general facility traffic, reliability improves dramatically. If you can't control the upstream network, then treat the panel edge as your boundary. Keep your field side communication deterministic inside the panel and connect outward through a well-defined interface. This is also where distributed Ethernet I/O helps you scale without making reliability worse. Instead of extending a serial bus farther and farther, you can place I/O closer to the panels and bring it back over Ethernet. Now, there are some great Ethernet I/O modules that'll actually fix this for you, like the PET7000 series and the ET7000 series. These are commonly used for this kind of modular expansion in industrial monitoring and control systems. And if you want to check out both of these products, the link will be in the description. Now, the value isn't just that it's Ethernet, the value is predictable expansion and easier isolation when problems happen. Now, the third Modbus TCP failure mode actually surprises people. They expect TCP to automatically mean fast, and then updates feel slow. Modbus TCP can support higher throughput, but scan performance still depends on polling strategy, register grouping, and timeouts and retries. If the master polls inefficiently, like reading small blocks repeatedly instead of reading contiguous blocks, you actually end up creating unnecessary traffic. If you set timeouts and retries poorly, you can either mask real failures or slow the system down in a way that's hard to diagnose. So the fix here is to be intentional. You want to group registers, use sane polling intervals, use realistic timeouts and retry counts, and test scan time under real load, not just with one device on a bench. Okay, so with all of that, what's the most reliable approach when you're dealing with real constraints like legacy RTU devices, electrical noise, and networks you don't fully control? Now, before I show you the architecture that solves most of this in practice, I just want to leave a reminder to please like the video if you're enjoying it so far. And if you are interested in seeing more content like this in the future, make sure you subscribe to the channel. All right, so here's the final approach that tends to be the most stable in the field. Build a hybrid architecture on purpose. Keep Modbus RTU where it makes sense. Short, controlled RS-485 segments close to legacy devices or noisy areas where serial wiring is already established. Then convert Modbus TCP for your backbone so you can scale, segment, and troubleshoot more easily. Use gateways at the boundary so RTU failures don't propagate across your entire system, and so TCP expansion stays clean. This pattern shows up everywhere in industrial monitoring systems because it matches reality. You don't always get to replace legacy RTU devices. You don't always control the upstream network, but you can control your architecture. And this is where ICP-DOS USA fits in, providing the building blocks that make this hybrid approach practical. Serial converters like the TM7561 for clean RS-485 connections during commissioning and support. Modbus gateways like the TGW700 series so that you can bridge RTU to TCP and isolate segments. And Ethernet I/O like the PET7000 and ET7000 series modules so that you can scale systems without turning the installation into a fragile daisy chain. So just to recap, Modbus RTU problems usually look like physical layer issues: wiring, termination, topology, and noise. While Modbus TCP problems usually look like network issues: IP planning, segmentation, and traffic behavior. And the most reliable systems are the ones that treat Modbus RTU, Modbus TCP, and Modbus gateways as architecture tools, not just best protocol choices. So let me know in the comments below about your device count, distance, and environment, especially whether you're dealing with VFD noise or a facility network you don't control, and I'll suggest whether RTU, TCP, or hybrid makes the most sense. And if you're wanting a deeper follow-up, the next video can be all about Modbus timeouts, retries, and scan strategy. Just let me know in the comments below. And if you're wanting an answer to a deeper question, you can always email our team at sales@icp-usa.com, or if you want to check out all of the solutions that we offer, you can head straight over to our website at icp-usa.com. Thank you so much for watching this video, and again, if you enjoyed, please make sure to like the video as it really helps out our channel. Thank you so much for watching.